So we are working today on learning about rational functions. And a rational function is basically something where we have a fraction. So we have an x on the denominator of our fraction. And we can have it written in this form here, where all of those a1, b1, a2, b2, those are all just numbers. And we have an x on the top and the bottom. However, that is not the form that we want to use the most often. We actually like to use this one the most often, because we know from our previous videos that the values of a, h, and k, those parameters, tell us a lot about the graph of our function, and it allows us to compare different rational functions. So we really want to be able to get into this second format here. So what we're going to look at in this video today is how do I go from one form into another. So if I look at this example here, I have an x on the top and on the bottom, and all of my x's are surrounded by different numbers, that a1, b1, a2, b2. And this is not my ideal form. I want to be able to transform it into this. So the way that we're going to do that is actually by using long division. So what we're going to see is how many times does this 2x minus 20 go into the numerator, that 10x minus 93? And maybe we'll be able to simplify this a little bit so that we don't have an x on the top of our fraction here. So let's set this up, 2x minus 20, and we're trying to figure out how many times that fits into 10x minus 93. So how do we start this? Well, the first question we ask is how many times does 2x go into 10x? And the answer to that is 5. So what I'd like to do next is just to write an expression that is my 2x minus 20 multiplied by 5. And we're going to be subtracting that away to see what we have as a remainder. So 5 times 2x is 10x, and 5 times negative 20 is negative 100. And now that I've got this, I can actually subtract, and I can figure out what I have left over. So 10x subtract 10x is 0. Don't actually need to write that down. That's the whole point of setting up this fraction in this way, or sorry, this subtraction in this way. And then we have negative 93, take away a negative 100. Well, that actually becomes negative 93 plus 100, which is actually 7. So what does that mean for our function? Well, it means that whenever I divide the denominator into the numerator, I end up with this remainder of 7. So it doesn't go completely. So I have this f of x is equal to 7. I have 7 left over 2x minus 20. And then I actually did have them divide into each other perfectly for 5. So I have 7, my remainder, over 2x minus 20, plus 5, because it divided in evenly 5 times. Now, if you look at this format, we're very, very close to what we're looking for. I already have an arrow drawn here. We're very, very close to that format, but there's one problem, and it's this. We have the number 2 here in front of our x. Our x is not isolated like it should be, according to this equation. So what are we going to do? We are going to try to transform this fraction. So we're going to multiply by the same number on the top and the bottom, or divide by the same number on the top and the bottom, so that'll transform the appearance of my fraction without actually changing the value of the fraction. So what I'm going to do is actually divide everything by 2. But if I divide this 2x by 2, I have to divide every single term. So what does that look like? Well, 7 divided by 2 gives me a 3.5. 2x divided by 2 is just an x. And negative 20 divided by 2 is a negative 10. So my fraction is actually still the same. Did not change that value of 5, but it changes the appearance of the fraction, so now I can actually figure out some information. So even though this is kind of a messy way to have this written, this is actually the last step that we need to do, because we want to be able to determine our a, our h, and our k. So our value of a is 3.5. Our value of h is 10. And our value of k is 5. And we'll be using that later on whenever we look at our graph of our function.